Hi, welcome to another system design video. In this video, we design a proximity service. What is a proximity service? This is a service that is commonly found as a back-end component in an app like Yelp to find the best restaurants nearby, or in a mapping app to find the closest gas stations. Let's first understand the problem and establish a design scope. Different apps may have different requirements for the proximity service. In this video, we designed this service as part of the business review app like Yelp. These apps have many features when it comes to searching for nearby businesses. It is not feasible to design all of them in this video. We'll narrow down the functional requirements to its core feature set. Here are what we came up with. 1. Given a user's location and a search radius as inputs, return all businesses within the search radius. 2. Business owners can add, delete, or update a business. These changes don't need to appear in real time. It is okay for the changes to appear the next day. 3. Users of the app can view detailed information about a business. Next, it is important to discuss the non-functional requirements. Non-functional requirements place various constraints on the design. Now, these requirements make the design interesting and challenging. Let's assume this review app has 100 million DAU and 200 million businesses. Now, what are some of the important non-functional requirements based on this scale? We came up with the following. 1. The latency should be low. Users should be able to find nearby businesses quickly. 2. The service should be highly available. It should be able to handle traffic spikes during peak hours. Now, let's do some back-of-the-envelope calculations based on the design constraints of 100 million DAU and 200 million businesses. It should give us a rough idea about some of the design challenges and trade-offs down the road. We need to make one more assumption in order to do this math, though. For a daily active user, on average, how many search queries do they make? Now, 5 queries per day seems like a reasonable number. So let's use that. With that, we can now calculate the search queries per second for this service. With 100 million DAU and 5 search queries per DAU, the search queries per second come to about 5,000. Now, we also need to get a rough idea how much storage we need to hold 200 million businesses. We'll defer this calculation until we know more about what the data schema would look like. Now that we have a pretty clear picture of the requirements for this service, let's look at the high-level design. In this section, we'll look at the API design, data schema, and we'll then walk through the high-level design diagram. First up, let's take a look at the API design for this service. Here we use the RESTful API convention. This keeps things simple. Now, based on the functional requirements we discussed above, we have 2 broad API categories. The first category is for searching nearby businesses. This is a single GET request that takes as input latitude and longitude of the user's location and an optional search radius. This API returns the business in an array of business objects along with the total count. 2 points to note here. First, we simplified the API for this short video by omitting pagination. In real life, though, we should include pagination in the API design. Second, the business objects in the API response contain just enough information to render the search result. It does not include enough information to render the detail page for a business. Now, to render the business detail page, another API endpoint is needed. This brings us to the other API category. The second API category manages business objects. It includes the CRUD endpoints to create, read, update, and delete a business. This is pretty standard for an API, and we won't go much deeper into it. Next, let's go over the data schema for the service. There are 2 key database tables for this. The first is the business table. This holds detailed information about the businesses. The primary key is the business ID. This table supports the CRUD operations for the business API we just discussed. The table schema is pretty straightforward. Now, the second table is more interesting. It is used by the Business Search Query API to return nearby businesses quickly. This table at the minimum should hold the business IDs and the locations of the business. The locations must be indexed in an efficient manner to produce search results quickly. The choice of this table and its database requires some knowledge of geospatial search. We'll dig deeper into this later. Now that we discussed the schema, we should be able to do some back-of-the-envelope calculation on storage requirements. Now, what do we know so far? There are 200 million businesses. For the business table, we estimate that all the details for a business should take no more than 10 kilobytes. On average, it would probably be closer to 1 kilobyte. So the business table should be in the low terabyte range. How about the table for nearby searchers? This table should hold the business ID, latitude, and longitude for each business. These are all 8 bytes each. That's about 200 million times 24 bytes, which is about 5 gigabytes. Now, this tells us that this data set for location search is tiny. When the database is this tiny, we have a lot of design options, including those that are purely in memory only. We're now at a point where we know enough to put together a rough high-level design diagram. In this system, there are 2 parts. They each map to an API category mentioned earlier. We call the first part location-based service, and the second part business service. Let's take a quick look at each component of this high-level design. First is the load balancer. In our design, the load balancer distributes incoming traffic across 2 services based on the API routes. As we'll see later, both services are stateless. Deploying stateless services behind a load balancer is pretty common, and we will not go much deeper here. Now note that in the real world, the company we work for might have other setups for distributing traffic to services. It could be Envoy in a Kubernetes cluster or API gateway on AWS. The exact details doesn't matter that much. Behind the load balancers are the 2 services we mentioned earlier. The location-based service is the core part of this system. It finds nearby businesses for a given search radius and location quickly. The location-based service has a few interesting characteristics. First, it is read-heavy with no write request at all. Second, the QPS is high. 5,000 QPS was our earlier estimate. Third, the service is stateless. It should be easy to scale horizontally. Next is the business service. The business service is the other service behind the load balancer. This service handles the CRUD requests for managing the business objects. The QPS for the create, update, and delete portions of the API is not high. And based on our functional requirements, the changes also don't need to take effect right away. This gives us a lot of flexibility on the design. For reads, though, the QPS could be high during peak hours. Since this data doesn't change frequently, it will be a great candidate for caching if necessary. Now, more on caching later. Next in the high-level design diagram is the database cluster. We have not discussed what kind of database we would use. We'll visit that topic in the deep dive. However, based on the access patterns and the read-write query volume, we already know enough to take a crack at what database topologies to use. Let's summarize what we know so far. The services are read-heavy. The read QPS is much higher than the write QPS. The writes don't need to be immediate. The search data set is not very large at all. The business data set is a bit bigger, and we might need to optimize it. We will revisit that in a bit. Based on these observations, using a database cluster with primary-secondary setup seems to be a good starting point. Now, in this configuration, the primary database handles all the write requests, and the read replicas handle the heavy read requests. Data is saved to the primary database first and then replicated to the replica. There will be some data inconsistency caused by replication delay, but since the changes to business don't need to be reflected in real time, the inconsistency is not a problem. At this point, we have a good idea what the overall system looks like. Let's dive deeper into a few interesting areas. Let's discuss what database to use to power the location-based search. There is a class of databases called geospatial databases that is optimized for storing and querying data in geometric space, like location data. Some examples of these databases are Redis GeoHash and Postgres with PostGIS extension. To understand at a high level how these databases work, we'll take a bit of a detour and discuss the common algorithms behind the geospatial index that powers these databases. This knowledge could help us choose the right solution for production environment. The most intuitive but inefficient way is to draw a circle and find all the businesses within the circle. Now, this pseudo SQL query shows us how we'll implement something like this in a database. The where clause looks a bit complicated, but it basically finds all the businesses that are within the bounding box specified in the where clause. The thing that jumps out is that this query is not efficient. It requires a table scan. With 200 million entries, it is slow. Now, how do we improve this? One idea is to build indexes on the longitude and latitude columns. Will this make it more efficient? The answer is, well, not by much. Let's see if we could spot the problem. Here we have two-dimensional data. The dataset returned for each dimension is huge. We could retrieve all businesses within a longitude range or a latitude range. But to fetch businesses within a search radius, we need to find the intersection of those ranges. This is inefficient because each dataset still contains a lot of data. Looking at it another way, the root problem with this approach is that the index can only improve the search speed in one of the two dimensions. Naturally, the follow-up question is this: can we map two-dimensional data into one dimension so we can build a single index on it? The answer is yes. There are two general approaches when it comes to geospatial indexing. The first approach is hash-based. Some examples are EvenGrid and GeoHash. The second approach is tree-based. These include Quadtree and Google S2. Even though the underlying implementations of these two broad approaches are different, the high-level idea is the same. They divide the map into smaller areas and build indexes for fast search. Let's explore the hash-based solutions first. One simple approach is to evenly divide the world into smaller grids. One grid could have many businesses, and each business belongs to one grid. This approach has one major issue. The distribution of businesses is uneven. There could be lots of businesses in downtown New York, for example, while in rural areas there could be very few businesses. Ideally, we want to use more granular grids for dense areas and larger grids for sparse ones. GeoHash is an improvement to the evenly divided grid. It works by reducing the two-dimensional location data into a one-dimensional string of letters and digits. Now, what does that really mean? Let's go over how GeoHash works at a high level. First, it divides the world into 4 quadrants along the prime meridian and the equator. These 4 quadrants are represented by 2 bits. For the first bit, the left half is 0 and the right half is 1. For the second bit, the top half is 1 and the bottom half is 0. Next, it divides each grid into 4 smaller grids. Each smaller grid is again represented by another 2 bits. The bits for the subgrids are appended to the existing bits. It repeats the subdivision and keeps adding more bits to the GeoHash. It stops subdividing when the subgrid reaches the desired size. Here is an example for the grid that contains the Google headquarters. In this case, the grid size is 1200 meters by 600 meters. Instead of using a long series of ones and zeros to represent a geohash, it is encoded as a base 32 string. Here, that long binary number is converted to a base 32 string with 6 letters. Now, to look at it from another angle, the base 32 encoded string length determines the size of the grid. These are called precision or levels, and there are 12 of these levels. For the location-based service, we're only interested in length 4 to 6. For anything longer than 6, the grid size is too small. If it is smaller than 4, the grid size is too large. Now, how do we choose the right precision given a search radius? We want to find the minimal geohash length that covers the whole circle. For example, if the radius is 2 kilometers, the geohash length should be 5. Another nice property is that geohash is just a string. Searching all businesses within a geohash is very simple. It means that any database could work. We don't need to use a special geospatial database. We'll talk about how to use geohash in a relational database in a little bit. Geohash works great most of the time, but there are some edge cases we should discuss. These edge cases have to do with how boundaries are handled. If two geohash strings share a long prefix, we know they are close. For example, here are some grids that share the prefix 9QXZN. However, the reverse is not true. Two grids could be right next to each other, but have no shared prefix at all. This is because the grids on either side of the equator or the prime meridian are in the different halves of the world. For example, these two French cities are only 30 kilometers apart, but their geohashes share no common prefix. Another boundary issue is that two locations can have a long shared prefix, but they are in two different geohashes. In this example, the green and red dots share 5 letters of the geohash strings, yet they're in two different grids. A common solution to both of these issues is to fetch the businesses not only within the current grid, but also from its 8 neighbors. Calculating the neighboring geohashes is not difficult. There are libraries to handle that in constant time. This concludes the exploration of hash-based geospatial indexing. Next, we will briefly look at the tree-based implementation. In this video, we will not implement the location-based service using any tree-based index, but it is good to understand at a high level how they work. The common tree-based indexes are Quadtree and Google S2. A quadtree is a data structure that partitions a two-dimensional space by recursively subdividing it into 4 quadrants. The subdivision stops when the grids meet certain criteria. In our use case, the criterion can be to keep subdividing until the number of businesses in the grid is no more than some number, say 100. A key point for Quadtree, and any other tree-based indexes for that matter, is that it is an in-memory data structure. It is not a database solution. This means that the index is built by our own code and runs on the location-based servers. This is a very different approach with a different set of deployment and operational constraints. For our design, we will focus on using geohash instead. Okay, so back to geohash. We want to use geohash as the geospatial index to speed up the location search. How do we structure the geospatial index table? At its core, the table only needs to have 2 columns, geohash and business ID. And any relational database can handle geohash. We don't need a special geospatial database for that. The geohash column contains the geohash of the right precision for each business. Converting a location in latitude and longitude to a geohash is straightforward. There are plenty of libraries to handle that. 2 things we should discuss with this table schema. First, many businesses will share the same geohash. This means different business IDs within a geohash are stored in different database rows. And the geohash and business ID columns together form a compound key. With the compound key, it makes removal of a business from the table efficient. Second, as we discussed earlier, For our application, we're interested in geohash with precisions 4 to 6. They correspond to different search radii from 0.5 kilometers to about 20 kilometers. The geohash column in the table will all have a geohash precision of 6. We'll use the light operator in SQL to search for shorter prefix lengths. Now here's an example. With this query, we find everything that is within the geohash of 9Q8ZN. Next, let's talk about how to scale the geospatial index table. Do we actually need to scale beyond one database for this table? Well, let's do some quick math. For this table, each geohash is 6 characters long. And let's assume that the business ID is 64 bits, so that's 8 bytes. Optionally, we may also want to store latitude and longitude for each business, so that it's easy to calculate the distance of each business from the user. So let's add another 16 bytes to it. So each row is about 30 bytes. With 200 million businesses, the total table size is about 6 gigabytes. This is tiny for modern hardware. The entire dataset can easily fit in a single database server. However, our read QPS at 5000 is quite high. With peak time spikes, a single database might not have enough CPU or network bandwidth to handle all the read requests. Now, what are some of the ways we could spread the read load? There are 2 general approaches. We can add read replicas, or we can shard the database. Sharding is more complicated. It requires sharding logic in the application layer. In our case, the entire dataset can fit in a single machine. There is no strong reason to shard. A better approach for us is to have a series of read replicas of the geospatial index table to help with the read load. This method is much easier to maintain than sharding. The last point we would like to touch on is caching. Do we need a caching layer in a design? It is not obvious if caching is a win. Our workload is read heavy, and the geospatial dataset is small. As we just discussed above, if read performance is the bottleneck, we can add read replicas to help. However, there's another dataset in our design. It is the business table. We estimated earlier that the dataset for the business table with 200 million businesses is in the terabyte range. For modern hardware, it is not that large. The dataset size is on the borderline where sharding might make sense. For this table, the update rate is slow and it is read heavy. We should be able to get away without sharding if we put a cache in front of it. This cache would take most of the read load of the frequently accessed businesses, and it should give the business table quite a bit of headroom to grow. Adding read replicas could also help with the read load. We have a lot of options for the business table. Our recommendation is to first ship it with a single database. As the product grows, and with the help of good monitoring, we can react to the growth and usage patterns and decide later on either to shard, add replicas, or add a cache in front of it. Now for this video, we'll omit the cache layer. Let's recap by tracing the life of a search request through our final design. Bob tries to find restaurants within 500 meters. The client sends the location and search radius to the load balancer. The load balancer forwards the request to the location-based service. Based on the location and the search radius, the service finds the geohash precision that matches the search request. 500 meters mapped to geohash length of 6. The service calculates the neighboring geohashes. There will be a total of 9 geohashes to query against the geospatial index table. The service sends a query to the database to fetch the business IDs and their lat-long pairs within those geohashes. The service uses the lat-long pairs to calculate the distance between the user and the businesses, rank them, and return the result to the client. Now that's it for the design of the proximity service. If you'd like to learn more about system design, check out our books and weekly newsletter. Please subscribe if you learned something new. Thank you so much. We'll see you next time.